Welcome to Part B of Unit 2 for our course on statistics. And we've been going through 3 different types of studies about means. And in our last section, we looked at a single sample test. That was a situation where we calculated just a single mean from a single sample. And now we're going to look at something called a paired sample study or a paired samples test. And this is a type of study that can be called many different things. So we could call this a paired sample study, or it could also be called a matched sample study, or a repeated measure design, or a difference score, a study about difference scores. And so paired samples, matched samples, repeated measures, difference scores, these are all terms for the exact same type of study. And hopefully as we go along here, it will become clear why all these terms refer to the type of study that we're talking about, how they all describe the same thing. Now, notably in our previous section, when we looked at a single sample test, recall that we were testing a null hypothesis that was somewhat of a silly null hypothesis to test. In that section, we were testing the null hypothesis that in the population, the mean was 0. And that was kind of a silly hypothesis to test because it would be difficult to think of a situation where that would address an important research question or why we would ever expect the mean for some variable to be exactly 0. But now with a paired samples design, this is actually going to be what we might call a special version of a single samples test. And it's a special type of single sample test where the null hypothesis is actually something meaningful. So a paired samples test in many ways is simply a particular version of a single samples test that has a null hypothesis that is meaningful. It's something we actually want to test. So let's take a look at a paired samples study. So a paired samples study is a type of study where I assess a sample of people on a single variable, but I assess them at 2 points in time. Or more precisely, it's a type of study where for each case I have 2 assessments of the same variable. And the most common example of a paired samples design is where people are assessed both before and after a treatment to see if they improved after the treatment. So, for example, maybe I have a new treatment for depression, and I deliver this treatment to a sample of clients who are suffering from depression, and I assess their levels of depression before receiving the treatment, and then I assess their depression again after receiving the treatment to see if they improved over time. Or maybe I have a treatment that I call fashion therapy, and this treatment is for people who experience a lack of self-confidence and they suffer from self-doubt. And so I get a sample of people who suffer from self-doubt, and I assess their level of self-doubt before treatment, and then I deliver my fashion therapy treatment to all the participants, and then I assess their level of self-doubt after the treatment. For example, there are 5 people depicted on the screen here, and maybe this was my sample of people who completed my fashion therapy treatment for self-doubt. Notably, these were actually pictures that came up when I did a Google search for the words before and after. And one thing that is noticeable about this sample is that they are all white women. And if this were an actual study, it would be important to have some kind of reason for why I am only including white women in the sample. And I might take this moment to note that there has been a history of racism within psychology research, where researchers have often conducted studies that included only white people or that overrepresented white people, and these researchers have often failed to notice the omission of people of color in these studies. And so, if for some reason only white people were volunteering to participate in my study, that would be a problem I would need to address. So hopefully these pictures then can serve two purposes. They can provide an example that we can use for our discussion of a paired samples test, and they can be a reminder of the fact that white people are often overrepresented in research, and when they are, this is a problem that needs to be fixed. So say I do my paired sample study with this sample of 5 women, and they all receive my fashion therapy, and I want to investigate the extent to which their self-doubt changes over time. And so self-doubt will be the X variable in my study. X will be self-doubt. It will be their score on a measure of self-doubt. So maybe I give them a questionnaire to measure the extent to which they suffer from self-doubt. And in a paired samples design, I'm going to assess self-doubt on 2 occasions. So maybe I assess their self-doubt once before they receive my fashion therapy, and then I assess their self-doubt again after they receive my fashion therapy. This means every person has 2 scores on self-doubt. I could call it X1 and X2, or X pre-treatment and X post-treatment. And now what I can do is I can calculate a different score, where I'll take their score for X at time 1 and subtract from it their score at X at time 2 to get the difference between their 2 self-doubt scores. And that would indicate the extent to which their self-doubt is changing over time. So for every single person in the sample, every single person has a score on X at time 1, and they have a score on X at time 2. They have their pre-treatment self-doubt score, and they have their post-treatment self-doubt score. And then for every single person, I can calculate this different score, which I symbolize by X minus X, which is their pre-treatment self-doubt minus post-treatment self-doubt, which tells me how much their self-doubt changed over the course of treatment. So every single person, we have a score, we have this X minus X, this different score, which is their pre-treatment self-doubt minus post-treatment self-doubt. Now, notably, what I'm describing here is a study investigating different scores. And if you recall our discussion from Unit 1, you should be able to identify if this study is correlational research or experimental research. So if I'm using this type of paired samples design, if I'm investigating different scores, that is, if I'm investigating the extent to which participants change over time, is this correlational research or experimental research? And the answer is this is correlational research and not experimental research. Recall that experimental research requires manipulation. A researcher would need to randomly assign participants into treatment and control groups for this to be experimental research. However, in this example, all participants received the treatment. There was no random assignment, so this is correlational research. This means that this type of study could not determine whether my treatment was effective. Now, people might improve during the time while they are receiving my treatment. Their self-doubt might go down over time, but that would not mean that my treatment was responsible for causing the improvement. Just because their self-doubt changes over time doesn't mean that my treatment was the cause of that change. To test whether my treatment was actually causing the change, to test the effectiveness of the treatment, we would need to conduct an experiment or a clinical trial where people are randomly assigned to treatment and control conditions. However, clinical trials can be very expensive and difficult to conduct. So, often a paired sample study investigating different scores, like what we're looking at here, this type of thing is often used as a rather valuable starting point. We could first do a paired sample study to see if at least people do improve during the treatment. And if they do, that wouldn't prove that the treatment is effective, but it certainly would look promising, and that might suggest it could be worthwhile to invest the time and money in conducting a clinical trial to provide a more definitive test of treatment effectiveness. So while a difference score study cannot demonstrate cause and effect, and it cannot determine whether our treatment is effective, it often is a very useful starting point as maybe the very first type of study we do when we want to investigate a treatment. So let's look at how we would calculate results if we have a paired samples design. And here is a hypothetical data set that we could use as an example for describing a paired sample study. So I've got my 5 women that completed my fashion therapy, and as before, I'm going to put each case on a separate row, so each person goes on a separate row. And in this type of study, I've got each person has a score on the x variable at time 1. So I have one column, x with a subscript 1, that's their score on x at time 1. And then we assess them a second time at time 2. So time 1, x1, that would be their score on self-doubt at time 1 before treatment. And x2, that's their score on self-doubt after treatment. And then I have a third column, which will be for that difference score, x minus x, x at time 1 minus x at time 2. I put DIFF up here to clarify that's a difference score. So we have our first case, say she got her self-doubt score was a 9 at time 1. At time 2, it went down by 1 point to an 8. And so 9 minus 8, it's a difference of 1. Her score went down by 1 point. Our next person, she had a score of 8 at time 1. It dropped down to a 5 at time 2. So her self-doubt dropped by 3 points. It went down by 3 points. Her difference score is 3. So this means every single person has a score for x at time 1. Every single person has a score for x at time 2. And every single person has a different score, which is your time 1 score minus your time 2 score, x1 minus x2. Note that in this example, we essentially have 3 different x variables that we could look at. We have x1, which is each person's score on self-doubt pre-treatment. We have x2, which is each person's score on self-doubt post-treatment. And then we have the difference score. That's the extent to which each person changed across the 2 time points. So we've got 3 variables, x1, x2, and a difference score. And we could calculate a mean and a standard deviation for each one of these 3 variables. So for example, let's take x1. We've got each person's score on self-doubt at time 1. And we've got scores of a 9, 8, 7, 4, and 3. And we could calculate the mean of those 5 values. It turns out the mean is 6.2. So the average level of doubt at time 1 is 6.2. And then we could calculate the standard deviation for x1. And if we calculate the standard deviation, we would discover in this example, it's 2.6. So for x1, it has a mean of 6.2 and a standard deviation of 2.6. Now we could do that same thing for x2, our second variable. We could calculate the mean and the standard deviation. And it turns out if we did that, we would discover that the mean for x2 is 4.2 and the standard deviation is 2.6. I actually made this come out nice and neat, so they actually both have the same standard deviation. So our standard deviation at time 1 and time 2 both turned out to be 2.6. Although notably, their scores on average dropped by 2 points. Their self-doubt went down by 2 points. We had 6.2 the first time. The second time their average is 4.2, so their self-doubt went down by 2 points. Now, an important thing that's key to understanding a paired samples test is the fact that we have a third mean and standard deviation that we could calculate. So we could calculate the mean and standard deviation for time 1, for x1. We can calculate the mean and the standard deviation for x2. And, here we go, we can calculate the mean and the standard deviation for the difference score. So I can, let's do that. Let's take, we have these different scores. We have a 1, a 3, a 3, a 1, and a 2. So if we add those up and divide by 5, we will have the average difference score. It turns out that the average difference score is equal to 2, as we can see up the top there. Here I put x bar, and I put DIFF right down below here. I have a subscript DIFF just to clarify that's the mean for the difference score. So x bar 1, that was our mean at time 1, x bar 2, that was our mean at time 2, and x bar DIFF, that's the mean for our difference score. So if we take these difference scores and add them up, divide by 5, we will get the average difference score, and the average is 2. And actually, it will always come out this way. Note that I just noted that the difference, if we take time 1 mean minus time 2 mean, x bar 1 minus x bar 2 is equal to 2. 6.2 minus 4.2, the difference is 2. And our mean difference score is 2. And it mathematically will always come out that way, that the difference between time 1 and time 2 will always be the same as your mean difference score. So our mean difference score is 2, and we can also calculate a standard deviation for these different scores. So we can take all these different scores and we could center them, and then we could square those centered deviations to get our sums of squares, and then we could divide that by degrees of freedom to get our variance, and then take the square root, and we would have the standard deviation of these different scores. And this comes out really super neat. It turns out that and I just made this come out this way, so the standard deviation of the different scores turns out to be exactly 1. So I have that up in the upper right hand corner. So we've got 3 different types of means and 3 different types of standard deviations. We have the mean at time 1, which is 6.2. We have the mean at time 2, which is 4.2. And we have the mean difference score, which is equal to 2. And we have 3 different standard deviations. We have the standard deviation at time 1, which is 2.6. We have the standard deviation at time 2, that was also 2.6. And we have the standard deviation of the different scores, and that was equal to 1. So, to do a paired samples analysis, I'm simply going to do a single sample analysis using this column of difference scores. So in the previous unit, we talked about a single sample study, and we talked about a situation where we were calculating just a single mean on a single variable. Well, that's all we're going to do here. We're going to calculate a single mean for a single variable, and that variable will be this difference score. We're going to calculate a single mean for our difference score, and that mean will be important because it will tell us how much people changed on average from time 1 to time 2. So we're simply going to do a single sample study design where we calculate a single mean on a single variable, and that single mean will be this difference score, the mean for our difference score. So we're essentially going to ignore everything in column 1 and column 2. We need we need x1 and x2 to be able to calculate our difference score, but then once I calculate my difference score, we can just forget about everything in column 1 and column 2, and now we just have a single variable, which is this difference score, and we're going to do a single sample study with this difference score. And so we can talk about the linear equations that we can use to answer the important questions at hand, and we can talk about how to calculate the standard error of our statistic, and we can talk about how to calculate a t-value. And as we go through that, you will see that what I'm talking about will be exactly the same as what we did for a single sample study. We're just conducting a single sample study here with one exception, and that one exception is that every time I talk about x, I'm going to clarify that x is a difference score. So we're simply going to do a single sample study where every time I mention x, I'm going to clarify that x is a difference score. So here we have our linear equations, and you will note these linear equations are the exact same equations that we saw in our previous unit, except for I've added the subscript DIFF all over the place to clarify that all these things pertain to difference scores. So we can read these equations as saying the difference score for individual I in sample S is equal to the mean difference score for sample S plus the error difference score for individual I in sample S, and that the mean difference score for sample S in population P is equal to the true population parameter difference score, mu, for population P, plus the error difference score for sample S from population P. So that's the exact same equations we saw in the previous unit. I'm just adding the subscript DIFF to clarify that everything's pertaining to difference scores. So given that we've seen this before, you should be able to identify which of those equations was the equation for variance in a sample, and which of those equations was an equation for sampling error variance in a population. So the top equation, that was the equation for variance in a sample, looking at how far different scores from individual cases deviate from the sample mean difference score. And the second equation, that was the equation for sampling error variance in a population, looking at the extent to which the parameter estimate for the difference score from our sample deviated from the true population parameter difference score in the entire population. And also in that top equation, the equation for variance in a sample, within this equation, you should be able to identify which components of this equation are variables and which component is the parameter estimate. And so x and e, those are the two variables, and the x bar, the mean, is the parameter estimate. And again, we can also identify that by the subscripts, because if it has a subscript is, that stands for the difference score for individual I in sample S. And because there's an I there, that means that different individuals can have different scores, which means it's a variable. And likewise, E, that's how far each person's difference score deviates from the sample mean difference score. And we have the letter I there to say that each person can have a different error. Each individual can have a different error. So the X difference score and the error difference score, they both have subscripts is to indicate that they're variables. The individuals can vary from one to another in their difference scores, and they can vary from one to another in their error. But there's only one mean in our sample. This is the mean difference score for sample S, and so there's no I there, and that's our parameter estimate. And that's the thing that we pull out of equation 1 and plug into equation 2. So we have our mean difference score in equation 1, the equation for variance in a sample, how far people deviate from the sample mean, and we plug that into our equation 2, our equation for sampling error variance in a population. It becomes the outcome, and we say the mean difference score for our study is equal to the true population difference score plus the error, how far our study deviated from that true population parameter. So you see, these are the exact same linear equations we saw in our previous unit. I'm just clarifying here that X is a difference score. And just as we did for a single sample study, for a paired sample study, if I give you an example and a data set, you should be able to fill in the numerical values for our linear equations. So for example, let's take this top equation. That's the equation for variance in a sample, how far cases deviate from the sample mean difference score. And then let's look over at our data set here and recall that after we calculate this difference score and get a column of difference scores, we can at that point just ignore these first two columns. We're not going to be using x1 and x2. We're going to be focusing on the column of difference scores from this point on. And then we could say, what is this first equation for case 1? So for case 1, what is this top equation, the equation for variance in a sample, how far cases deviate from the sample mean? So the difference score for case I from sample S, if we're focusing on case 1, her difference score was a 1. And so I'm going to plug that in right there. And we're going to say the difference score for individual I in sample S is equal to the mean difference score for sample S. And we calculated that the mean for this sample, the mean difference score, was a 2. So I'll plug that in right there. And then if the mean was a 2 and she scored a 1, that means she's 1 point below the mean. So the error difference for individual I in sample S for case 1, her error is a -1. She was 1 point below the sample mean. So that equation for case 1 is 1 equals 2 plus -1. And then we could do the same thing for our second equation for sampling error variance in a population, looking at how far the mean difference score from our sample deviates from the true population parameter. And for this example, as always, we're going to assume that the null hypothesis is true. So for this example, if we assume the null hypothesis is true, what are the numerical values for that second equation for sampling error variance in a population? So the mean difference score for sample S from population P, for this particular sample, that mean difference score was a 2. So I'm going to take that 2 and I'll put that right there. And we're going to say 2 is equal to the true population parameter, and we're going to assume that the null hypothesis is true. So I'm going to put a 0 right there. And if the true parameter is 0, and this study got a 2, that means that we were 2 points above the true population parameter, so the error for this study would have been a 2. And that second equation takes this form that it will always take whenever we assume the null hypothesis is true. We're going to say our parameter estimate is equal to the true population parameter we assume is 0 plus whatever value is equal to our parameter estimate. So in this case, we have 2 equals 0 plus 2. So that's how we would fill in the numerical values for our two linear equations. And as we've done before, we can see how we can use these two linear equations to answer two key questions. One key question is the descriptive question, which is simply what is the parameter estimate for this study, for this sample. And the second question will be the inferential question about how well results from this study apply to the entire population. And as before, the descriptive question is simply what is the parameter estimate, and in this study we're looking at a mean difference score. That's the parameter estimate that we're calculating. That's the whole reason for doing the study, is that we want to know what that mean difference score is. And in our equations, we have that mean difference score, x bar diff for sample S, and it's the same mean right there. It's also the same mean right down here, x mean diff for sample S. And in our second equation, I also clarify it's from population P. And so this mean from our equation, the mean difference score from our equation, is the thing that answers that descriptive question, because that gives us our parameter estimate. And then the second question is the inferential question. That's the question of how well results from this sample apply to the entire population. And as before, we're going to answer that inferential question by focusing on this error from our second equation. That's the equation for sampling error variance in a population, looking at how far the mean difference scores from each sample typically deviate from the true population parameter. So that's the E, and then I have diff to clarify it's a difference score. So E diff SP, the error for sample S from population P. And we're going to be looking at these errors to answer that inferential question. And in the box, I have two questions we can address about those errors. The first question is, what is the average deviation of the absolute values of E diff SP? And the second question is, if the null hypothesis is true, what is the standardized E diff SP for this particular study? And these are the same questions I've asked before, and so you should be able to answer those questions. So first, what statistic tells us, what statistic answers this first question? What is the average deviation of the absolute value of E diff SP? What is the answer to that? Well, that is our standard error of our statistic. In this case, it would be the standard error of the difference score. And then second, if the null hypothesis is true, what is the standardized E diff SP for this particular study? What statistic answers that question? And the answer to that is a t-value. A t-value will tell us if the null hypothesis is true. The t-value tells us the standardized error for this particular study. In just a moment, I'm going to clarify how to calculate a standard error of difference score and how to calculate a t-value when we have a paired sample study. But before I do that, I want to expand our understanding a little bit about the places where it would be appropriate to calculate a paired samples analysis. So recall that I said we can do a paired sample study anytime I have a sample of cases and every case has two scores on the same variable. So we've been talking about a situation where every case is a person and each person has two scores, say one before treatment and one after treatment. But another place where we could do a paired samples design is where every case has two units or two parts to it. So on the screen you see a sample of heterosexual couples. And in this type of study, say I got a sample of 5 couples, and every couple was a heterosexual couple with 1 woman and 1 man in the couple. In this case, I could say every couple is a case, and each case has 1 woman and 1 man. And say, for example, I was wanting to investigate a gender difference in how people respond to interpersonal conflict in their relationships. So when a couple has a conflict, how do they respond? There's been some research in the United States suggesting that, actually at least in the United States, when couples have conflict, there's some tendency for men to be a little more likely to want to withdraw from the conflict, try to avoid the conflict or escape the situation. And women sometimes tend to be a little bit more likely to want to engage in the conflict, to address it, and to hash it out. So say we wanted to do a study investigating this possible gender difference between men and women and how much they tend to withdraw from conflict. So I could get a sample of 5 couples, and if I have 1 woman and 1 man in each couple, I could assess the woman for how much she withdraws from conflict and get her score on X. Her score on the X variable would be how much she tends to withdraw from conflict. And then I'd get a score for the man in the couple. That would be his score for how much he tends to withdraw from conflict. So now every case is a couple, and every couple has, we have 2 scores on the same X variable. The X variable is how much a person withdraws from conflict. That's X. And we have the woman's score on X, how much she withdraws from conflict. The man's score on X, how much he withdraws from conflict. And then we can calculate a different score for every single couple. We can calculate a different score for every single case in this sample. Every case has 2 units, a woman and a man, and we have the woman's score on X, the man's score on X, and so we can calculate a different score for every single case. And so in this example, a case is not a single person, the case is the couple. That's the unit of analysis. This would be an analysis where we're studying couples and not individual people. And so to reinforce that point, that when we do a paired samples analysis, each case actually has 3 different types of scores. Let's look at how that's true for these couples. So each couple is going to have 3 different types of scores. We'll have the score on X for the wife, we'll have the score on X for the husband, and then we'll have the different score, the wife's score minus the husband's score. So we've got X for the wife, X for the husband, and that different score. That means we can calculate 3 different means. Here I'll circle this as X bar with a subscript W. That would be the mean for the wives in the sample. So if I have a sample of 5 couples, what's the average score for the 5 wives in the sample? And then I could get the mean for the husbands in my sample. If I have 5 husbands, get the mean for the husbands. And then every couple has a different score, the mean for the wife, or the score for the wife minus the score for the husband. So we've got 5 different scores, and I could calculate what's the mean of the different scores for these 5 couples. And likewise, we can calculate the standard deviation for the wives' withdrawal scores. So each wife has a score on how much she tends to withdraw from conflict. And so we can calculate the mean for wife withdrawal and the standard deviation for wife withdrawal, and we get the SD subscript W. That's the standard deviation for wife withdrawal. And then we could calculate the standard deviation for the husband scores. SD subscript H would be the standard deviation for all the husband scores. And then we'll have this column of different scores. For each couple, we have their different score, the difference between wife and husband, wife's score minus husband's score, and we can calculate the standard deviation of those different scores. And again, when we're doing a paired samples analysis, we're going to, after we calculate our different scores, we're then going to ignore the individual scores for wives, and we're going to ignore the individual scores for husbands, and we're going to focus on the difference score. We want to calculate this mean difference score, and we're going to use actually this standard deviation of the different scores. We're going to use that in our calculations, as we'll see in just a moment, when we need to calculate our standard error of the difference score. So now you have a couple examples of where we could use this paired samples analysis. We could do this if we had the usual way, where we have people in a sample and every person is assessed on 2 occasions, like prior to a treatment and after a treatment, but we could also use this paired samples approach if I have couples and each couple has 2 identified parts to it. And here is the formula to calculate a t-value for a paired sample study. And you will note that this formula is the exact same formula as the formula I showed you in the previous unit for a single sample study, with the exception that I am now clarifying that X is a difference score. Otherwise, it's the same formula. So we have the t-value as being equal to the mean difference score for our sample. So say I get a sample of 5 couples and I calculate the average difference score. That's my statistic. So I get the mean difference score for my sample. I subtract from that the true population parameter, which I'm going to assume is 0. I assume that mu, the true population mean difference score, is 0. And so I take the statistic from my study and subtract from it the true population parameter, divide it by the standard error of my statistic, that is the standard error of the mean difference score, and that will always simplify to my statistic divided by its standard error, the mean difference score divided by the standard error of mean difference score. And as always, once I give you this t formula and say we calculate a t-value as taking our statistic divided by the standard error of our statistic, then you ask the question, well, what formula can I use to calculate the standard error of the statistic? In order to calculate the standard error of my statistic, I'll need a formula to do that. What formula can I use to estimate the standard error of a mean difference score? And here is the formula you can use to calculate the standard error of a mean difference score. So our notation is we have SD with a subscript x bar difference. That stands for the standard deviation of the sampling error of mean difference scores, or we call that the standard error of mean difference scores. Sometimes I shorten it just to standard error of mean difference, or I could say it the long way and say it's the standard error of mean difference scores. And that's equal to the standard deviation of difference scores divided by the square root of n. Now that equation should look very familiar to you. Note, this is actually the exact same equation I gave you in the previous unit where we were talking about single sample studies. This is the equation I gave you for the standard error of the mean. With one exception is that in this example, now I'm clarifying that we're dealing with a mean difference score. This is not the standard error of just any old mean. This is the standard error of mean difference scores. So I'm just clarifying we're dealing with different scores. Otherwise, it's the same equation. So in the previous equation, in the previous unit, when I gave you the standard error of a mean, and I didn't clarify what type of mean we were talking about, I just said our standard error of the mean was equal to the standard deviation divided by the square root of n, and I didn't clarify a standard deviation of what. Now I'm clarifying we're dealing with a standard deviation of difference scores. And so I'm just adding that clarification, otherwise it's the same equation. Let's clarify exactly what I mean by the standard deviation of difference scores, just to make sure you know what needs to be plugged in here. Let me go back to that previous slide showing our data set, what a data set might look like for a paired sample study. And so recall that if I'm doing a paired sample study, every case has a score on x1, every case has a score on x2, and every case has a different score, which means we can calculate the mean and the standard deviation for the first x variable. We can calculate a mean and a standard deviation for the second x variable, and we can calculate the mean and the standard deviation for the different scores. And recall that I said when we do this paired samples analysis, after we calculate our difference scores, at that point we don't need x1 and x2. We're going to ignore them. So I can just scribble that out here. We're going to scribble all that out. And I don't need to know the mean or the standard deviation for x1 and x2 individually, because everything is going to focus on these difference scores. So when we calculate our standard error of mean difference score, which standard deviation do we plug into that formula? We don't plug in the standard deviation for x1. We don't plug in the standard deviation for x2. We plug in the standard deviation for the difference scores. In this example, it's that value of 1 is the standard deviation of the difference scores. So if I go back to our previous slide here, we take that standard deviation of difference scores, and that's the thing we divide by the square root of n. And so with that clarification, you'll note that this formula is otherwise the exact same formula that I gave you before. This is the formula for the standard error of a mean. With the clarification, we're dealing with a mean difference score. And so now you have everything you need to be able to calculate a t-value for a paired sample study. So the t-value is always equal to a statistic divided by its standard error. So in this case, we have our statistic is the mean difference score for our sample, and we're going to divide that by the standard error of mean difference score. And we can calculate the standard error of mean difference score using this formula on the middle of the page, the standard error of difference scores divided by the square root of n, and then we plug that into our t-score formula. So we can calculate the mean difference score divided by the standard error of mean difference score to get our t-value. And then once we have our t-value, we can determine the probability of that t-value. That is, we can determine the probability of getting a t-value that extreme if the null hypothesis is true. And to determine the probability of your t-value, we can look that up on a t-table, as I'll show you how to do in the lecture add-on videos. We can use a t-calculator or use software to calculate the probabilities of our t-values, or different ways for getting the probability. But however we do it, to get the probability of a t-value, we need two things. So to get the probability of a t-value, you first need to know what the t-value is, and then second, you need to know the degrees of freedom, because recall that the t-distribution changes shape just slightly depending on your degrees of freedom, depending on your sample size. So to get the probability, you need to know what is your t-value and what are your degrees of freedom. And in a paired sample study, your degrees of freedom will be equal to n minus 1. And you will note that's the exact same degrees of freedom I gave you for a single sample study. There, I also said degrees of freedom is equal to n minus 1. Now, with a paired sample study, sometimes that can be a little bit confusing to know what your sample size is. Your sample size is the number of cases. So if I had a sample of people and each person completed 2 assessments, maybe they completed a pre-test prior to receiving a treatment, and then they completed a post-test after receiving a treatment, and each person would have 2 scores on X. Each person has 2 scores, but I would only count each person once. And so if I had a sample of 5 people and each person completed an assessment prior to the treatment and after the treatment, because I have 5 people or 5 cases in my sample size would be 5. And so my degrees of freedom would be n minus 1, which would be 4. Now, the same thing applies if I had a sample of couples. If I had a sample of couples, like in the picture in the lower left-hand side of the screen here, if I had a sample of couples and I had a score, say these were heterosexual couples with a wife score and a husband score for every couple, in this case, the case would be the couple, not the person. I have one different score for every case. So if you want to figure out how many cases you have in a sample with a paired sample study, you can count the number of different scores because you will have one different score for every case. So if I have a sample of couples, each couple produces one different score. So each couple is one unit, one case. So if I was doing a paired sample study and I had 5 couples, I would say my sample size is 5. It's not 10. I don't count the people because in this example, the case is the couple and not the person. So I would have 5 couples. And so my degrees of freedom, if I had 5 couples, would be n minus 1, would be 4. So degrees of freedom, your sample size minus 1. And keep in mind that when you count your sample size, each case will produce one different score. And here is a slide using our hypothetical data set to illustrate all the things we've been talking about in this section on a paired samples analysis. And so here we have our two linear equations, and the top equation is the equation for variance in a sample. That's how far different scores from individual cases deviate from the sample mean difference score. And the bottom equation, that's the equation for sampling error variance in a population. That's how far the mean difference scores from our samples might deviate from the true population parameter difference score. And we've been looking at how we can use these equations to address or to answer the key questions at hand. And one of the key questions is the descriptive question, which is simply what is the parameter estimate for this study? And so in our equations, we have this mean difference score from sample S, and that's the parameter estimate. And that answers that descriptive question. That gives us the parameter estimate. And this was the whole reason for doing the study. We did the study to determine what is the mean difference score for this sample. And so if our mean difference score was 2, and we were doing this study where we were investigating the extent to which women changed in their levels of self-doubt, that would answer the key question at hand. That would tell us that on average their self-doubt went down by 2 units. Going from time 1 to time 2, on average their self-doubt decreased by 2 units. That's what it means if our mean difference score is 2. And so the other key question we want to address is the inferential question. That is, how well do the results from this sample apply to the entire population? And to address that inferential question, we focus on the errors from this second equation. These errors looking at how far the means from different samples deviate from the true population parameter, this diff subscript SP. And there were 2 different questions we could address regarding these errors. The first is, on average, how much error do we make? What is the average distance if we replicate our study over and over and over again? On average, how much will each mean difference score typically deviate from the true population parameter? And that's what's given by the standard error of the mean difference score. And we saw that we could calculate the standard error of a mean difference score by taking the standard deviation of different scores divided by the square root of n. So if we do that with this example, let's see what we get. So the standard error of mean difference score, we take the standard deviation of the different scores, and it turns out, as I mentioned before, the standard error of the different scores for this sample was equal to 1. And so I'm going to plug that in right there. That's our standard deviation of different scores divided by the square root of n. And so we have 5 cases in this data set. So we take 1 divided by the square root of 5, and we get a standard error of difference score of 0.447. So that means if we replicate our study over and over again, and each time we calculate a mean difference score, on average, each statistic we calculate, each mean difference score we calculate is going to deviate about 0.447 units away from the true population parameter. It's almost about a half a unit, not quite a half a unit of error we're likely to make on average across all our studies if we replicate it over and over again. And then once we have our standard error of mean difference score, we can then calculate a t-value. The t-value will tell us for this particular study how much error did we make in standardized units if the null hypothesis is true. And so for our t-value, we're going to take our statistic divided by its standard error. So our statistic was the mean difference score, that's a 2. So I'll take that 2 right there. Our standard error of our mean difference score was 0.447. So I'll plug that in right down here. 2 divided by 0.447, I get a t-value of 4.47. That means if the null hypothesis is true, we made more than 4 times the typical amount of error. That's a fair amount of error. And at this point, we could determine the probability of that t-value. And I'll show you how to do that, for example, on the lecture add-on videos, how we can actually use t-tables to calculate that. In this example, if I looked up what's the probability of getting a t-value this extreme if the null hypothesis is true, to calculate that probability, I would need 2 things. I need to know what is my t-value, it's 4.47, And I would need to know the degrees of freedom. And the degrees of freedom are going to be n minus 1. And so if I have 5 cases here, my degrees of freedom are going to be equal to 4. And so if my degrees of freedom are equal to 4, and if I were to go to a t-table and look that up, I believe the probability in this example would give me a probability, I think it's about 0.011 or something like that. So it would be a small probability, and this would be less than 0.05. So this would be significant, and we could reject the null hypothesis and claim to have discovered a non-zero effect. And go back and recall what I talked about, that when we're doing a paired sample study, the null hypothesis now is something meaningful, because the null hypothesis here is that the mean difference score is 0. And if the mean difference score is 0, that means there was no change. There was no effect. So with a paired samples study, even though we're doing all the same things as a single sample study, with a paired sample study, now we actually have a meaningful null hypothesis. The null hypothesis was that the true mean difference score in the population was 0, and a mean difference score of 0 means there's no change, no effect, no difference between x1 and x2. And so because this result, if I came up with a significant result here, my probability is less than 0.05, meaning if the null hypothesis were true, I would only get a t-value this extreme. It would be about once in 100 or so, and that's definitely less than a 5% probability. And so because my p-value is less than 0.05, I'm going to say this would be a very rare, unusual result to get if the null hypothesis were true, and therefore I'm going to reject that null hypothesis and claim to have discovered a non-zero effect. I'm going to claim I've discovered that indeed there was a change between time 1 and time 2 based on the results from my sample. Now, whenever you're doing a paired samples analysis, you're working with a very unique type of data set. Because recall that I said that to do a paired samples analysis, you need to have a sample of cases, and you need to have 2 scores from every case on the same variable. Every case needs a score on x1, and every case needs a score on x2. So we've got 2 scores from every case on the same x variable. So if I'm looking at this sample of women and I'm assessing the extent to which their self-doubt changed over time, I have their scores on self-doubt at time 1, and I have their scores on self-doubt at time 2. So I have 2 scores from every case on the same variable. And when I have this type of data set, there's actually 2 different questions we could address. So we've been looking at the question about whether there's a difference between x1 and x2. Or in the sample of women, that's a question about whether there was a change in their level of self-doubt from time 1 to time 2. And we've been addressing that question by looking at the mean difference score. We calculate a mean difference score to indicate the extent to which there was a change over time in their levels of self-doubt. That indicates the extent to which there was a change in their x variables. But there is also a completely different question we could address here, and that's a question that I will call the question of a paired sample correlation. And the question of a paired sample correlation asks whether x1 is correlated with x2. So we've got 2 questions here. One question is whether there is a change or a difference between x1 and x2. The second question asks whether x1 is correlated with x2. To illustrate what I've been talking about here, I've got 4 boxes on the screen, and each box is going to illustrate a different scenario, a different possible outcome we could get if we do a paired sample study. And each box is going to illustrate a different scenario in terms of whether or not there's a difference score, a difference between x1 and x2, and whether or not there's a paired samples correlation, whether or not there's a correlation between x1 and x2. So let's see what we have. In the upper left-hand corner, the first box I have here, I've got 2 columns, and let's say the first column is going to represent people's scores on X1, and the second column will represent people's scores on X2. So I have 4 faces in this first column. I've shrunk my sample size down to 4 to make everything fit on the screen. And so I've got 4 faces there, and let's say I've lined them up in their order for their score on the X variable. So if I'm measuring self-doubt, this person at the top, say that she had the highest score for self-doubt, and the person under her, say she had the second highest score for self-doubt, and then the third person, she had the third highest, and the person at the bottom, say she had the lowest score for self-doubt. So say I've arranged these faces to indicate where their scores were for levels of self-doubt. And so in this upper example, in the upper left-hand corner, in this box right here, I'm showing a situation where people's average self-doubt at time 1 was higher than their average self-doubt at time 2. So the second column would be the second assessment, and we're showing a situation where their scores at time 1 on average were higher than their scores at time 2. Their scores went down from time 1 to time 2. So this box is showing a situation where we have a difference. We have a difference between X1 and X2. Now note that's a different question about asking whether X1 is correlated with X2. And in this example, in the upper left-hand corner, this is showing a situation where we would have essentially a perfect correlation between time 1 and time 2. So notice the person who scored the highest at time 1 is also the person who scored the highest at time 2. The person who was second highest here also was second highest at time 2. The person who was the third highest remained the third highest, and the person who was at the bottom remained at the bottom. So I can say the rank order of the cases stayed the same from time 1 to time 2. And that's essentially what a paired samples correlation is testing. A paired samples correlation is testing the extent to which the rank order of cases stays the same across assessment points. So in this example, in the upper left-hand corner, we're showing a situation where we have a difference from time 1 to time 2, and we have a perfect paired samples correlation because the rank order of cases stays the same. Let's compare that with a box in the upper right-hand corner. So in the upper right-hand corner, that's again, we have a difference from time 1 to time 2. I have the scores at time 1. On average, these scores are higher than the scores at time 2. And on average, people's scores drop down going from time 1 to time 2 on average. So we would have a difference. But this box in the upper right-hand side is showing a situation where we do not have a paired samples correlation. This paired samples correlation would be close to 0 probably. So the person who is at the top, she became kind of towards the middle there. The person that was second highest became the highest. The person that was third from the bottom became the very bottom, and the person at the bottom went second to top. So if we draw the lines for how people's rank order stayed the same or not, we see that our lines get all crisscrossed and messed up here. So the rank order is not staying the same from time 1 to time 2. The rank order is getting all mixed up if you go from time 1 to time 2. So this example would be a situation where we do have a difference from time 1 to time 2, but we do not have a paired samples correlation. That correlation would be close to 0 because the scores are getting all mixed up. Now if we go to the bottom left has a situation where there's no change from time 1 to time 2. We do not have a difference. X1 is not different from X2. The average score for X1 is the same as the average score for X2. So their scores are not changing. Now in this lower left-hand example, we do have a paired samples correlation. People's scores at time 1, the rank order of cases is staying the same from time 1 to time 2. So this lower left example shows no difference from time 1 to time 2, but it does show a near perfect paired samples correlation. On the lower right hand side, we have a situation where there's no difference and no correlation. The average score for time 1 is about the same as the average score for time 2, so we have no difference. And if we look at how the rank order of cases falls for these two time points, they get all mixed up. Again, the person at time 1, they change their rank order, and if I'm drawing these lines, they crisscross all over the place. So this bottom right example would be a situation where we have no difference and no correlation. So putting it all together, the two examples on top are both showing situations where we have a difference, and the two examples on the bottom are showing situations where we do not have a difference. And the two examples on the left are showing situations where we have a paired samples correlation, and the two examples on the right are showing situations where we do not have a paired samples correlation. So this clarifies the fact that there's a difference between a paired samples correlation and asking about a difference between x1 and x2. If I'm calculating the mean difference score, that's answering one question, but I could address an entirely different question, which is the question of whether or not there's a paired samples correlation. And I can do this with a paired samples test because if I have a data set for doing a paired sample study, I have this very unique type of data set where for every case I have two scores on the same x variable. And when I have this unique type of data set, that's when I can do this. I can answer both these questions. I could say, is there a difference between x1 and x2? That's one question. Or I could say, is there a paired samples correlation? And that's a different question. And it's important to keep in mind that these are two different questions. They're not related to each other. Just because you have a paired samples correlation, that says nothing about whether or not you have a difference. If you have a difference between time 1 and time 2, or a difference between your two x variables, that says nothing about whether or not there's a paired samples correlation. So whenever you have a data set that you're using for a paired samples analysis, you need to keep track of the fact that there are these two separate questions you could address, and you need to keep track of what question you're actually addressing when you do your analysis. So that's an additional question we could address if we're doing a paired samples analysis. And that completes everything for part B of Unit 3.